PowerPoint presentation, and I will show you where I stopped last time. All right. We will have a test next week. I'm going to send an announcement about that on chapter 7 and 8. So let's finish chapter 8. And you need to go through questions and answers for chapter 7 and 8. It's already in the module 4. We talked about properties of water, hydrogen bonding, and also we talked about the distribution of water on Earth, ice caps, oceans, groundwater, surface water, etc. And we were talking about solutions containing, water solution containing various pollutants. So we were on slides explaining concentration of solutions, different solutions, parts per million, parts per billion, molarity. So we're going to continue from there. Today we're going to talk about acids and bases and about issues related to heartburns and titrations, how you quantify acidity, basicity based on pH scales, what causes acidity in water, and at the end we're going to look into treatment of water to produce fresh water for drinking and household use. Water also, we also going to talk about global challenges that are associated with maintaining water. So let me go to the slides where I stopped last time. We were talking about water solutions, how you prepare a solution using volumetric flask, how you prepare 1 molar sodium chloride solution. Volumetric flask, this flask with 100 milliliter capacity is a 100 milliliter volumetric flask. We have different sizes, 50, 100, 500, etc. Depending on the amount of solution you need, you pick up the certain volumetric flask and add moles of sodium chloride and volume of the sodium chloride calculated to give the desired molarity. This example shows 1 molar sodium chloride solution. 1 mole of sodium chloride solution contains 1 mole of sodium chloride in 1 liter of solution, or 1000 milliliters of solution. 1 liter is 1000 milliliters. The molecular weight of sodium chloride is 58.5. 23 plus 3.5, 35.45. Chlorine atomic mass, sodium atomic mass added to give 58.5. So you calculate 1 mole is 58.5 grams is 1 mole, molar mass in grams. You put that in the flask and add the water to flask about halfway, then mix it up until it dissolves everything. Then keep adding water up to the mark where the top of the volumetric flask. and then shake up and down to get the solution mix. So that's how you prepare different solutions with certain molarity. Now, we're going to look into some of the problems here. First, how you calculate molarity given a ppb, concentration of mercury 2+ ions in a solution. We're going to look into that. And also we're going to compare moles of solute present in each of the 1.5 molar and 0.15 molar sodium chloride solution. As you can see, 1.5 molar contains more moles. So you can calculate exactly. Thirdly, a solution is prepared dissolving 50 moles of sodium chloride in 250 milliliters. And second solution is 0.6 moles sodium chloride to 200 milliliters. You calculate the molarities of the solutions and compare which concentration is higher. We also going to look at the example of copper sulfate solution. Whether what student prepared was 1 molar, 2 molar copper sulfate solution. So we're going to look into that in little detail. So first, expression of 16 parts per billion mercury in units. So 16 parts per billion is weight by volume, okay? So normally we have weight by volume. So that means 16 grams in volume is, billion is 10 to the negative 9 milliliters. That's the mercury in 16. Now we convert that to milliliters, 10 to the negative 9 milliliters to liters. Okay, that is given in milliliters. So we come up with 1.6 10 to the negative 5 grams per liters mercury. So that's how you get grams per liter. Now to convert grams, 1.6 10 to the negative 5, you have to divide it by molar mass of mercury, which is 200.6. Mercury is 200.6. So you end up with 8.0 10 to the negative 2 moles per liter solution. So grams converted to moles. That's how you do the calculations. Now, the second problem, 1.5 molar and 0.15, how many moles are present in each? For the first solution, number of moles is half. 500 milliliters is half of a liter. Therefore, to get the number of moles in 1.5, I divide 1.5 by 2, get 0.75 moles. On the second solution, I divided 0.15 by 2, you get 0.075. So which one is how many moles? You can see the first solution has more moles of sodium chloride than the second one. Of course, the molarities are smaller for second solution. Molarity is also an indication of number of moles of solute. Okay, that's to give you an idea. Then the last two problems. A solution is prepared by dissolving 0.50 sodium chloride in enough water to form 250 milliliter solution. So first solution is, I calculate the molarity. 0.5 divided by 250 milliliters is 0.250 liters. Milliliters converted to liters by dividing 1000, 10 to the 3. So the molarity of the solution is 2 molar. On the second set, 0.6 moles divided by 0.200 liters gives molarity for the second solution 3 molar. Big M is moles per liter. So therefore, which solution is more concentrated? Second solution is concentrated. Explain. I did the calculation and came up with the answer. So only concentration is the direct indication of what is concentrated and what is dilute or less concentrated. A student was asked to prepare 1 liter of 2 molar copper sulfate solution. The student placed 440 grams of copper in volumetric flask and filled it to the level 100,000 milliliter mark. Was the resulting solution 2 molar? I'm going to check whether what he dissolved, how many copper sulfate moles are there, then divided by liter of solution or 1000 milliliters. His answer is no. How? If you divide 40, that's 159.55 is the molar mass of copper sulfate. 1 mole of copper sulfate contains 159.5 grams of copper sulfate. So the molarity is 0.25 moles per copper sulfate. Therefore, it is not 2 molar. The answer is no. It's not. Was the resulting solution 2.0? If you were to get the 2.0, it has to be at least more sodium, more copper sulfate dissolved in the solution, right? So all right. So let's go to the next slide. So it's copper sulfate is solution is 0.250. Now we're going to talk about ionic compound and their solubilities. Ionic compounds goes into water solution because water is polar. Water has negative poles, and on oxygen, on the water molecule has negative poles, on hydrogen has positive poles. When you dissolve sodium chloride here in the picture, the sodium ions are small ones, the black ones, or purple, whatever the color is, and the green ones are the chloride ions. The way the water is oriented, you can see their dipoles are pointing towards the opposite charges. Sodium ions are facing negative ends of the dipole. Chloride ions are facing the positive hydrogen side of the dipole. They are surrounded by. This process is called solvation or hydration, surrounded by water molecules. The energy that's required to break up sodium chloride is provided by solvation energy. Therefore, sodium chloride is soluble. 90% of water on the planet is found in the salt water of oceans. See, this is how the sodium chloride is dissolved in seawater. If you wanted to get sodium chloride from seawater, you pump seawater into reservoirs close to the ocean and let it dry. The sun will evaporate sodium water and produce sodium chloride. That's how we get salt produced. Major way to produce salt is from seawater. Since water is polar, partial negative charge on the oxygen and partial negative charge on the hydrogen, the negative charges surround the sodium ions, as I described before. The partially positive charge on the hydrogen atom surround the chloride ions. So when sodium chloride goes into water solution, it dissociates, ions are dissociated. That's what you mean by dissociation, breaking up. Soluble and solvated aqueous sodium ions and chloride ions are produced. Dissolved in the salt to form its component ion is called dissociation. Dissolving is dissociation. There are ionic compounds containing polyatomic ions. They also dissociate into polyatomic ion, and identity of the polyatomic ion remain intact. For example, sodium sulfate. Sodium is monoatomic, only one atom, sodium ion. Sulfate is a polyatomic ion, so it produces 3 ions per sodium sulfate. 2 sodium ions, solvated sodium ions, and similar to sodium chloride, they also undergo hydration or solvation with water. Notice 2 sodium ions in the compound dissociate to form each other as well, forming total 3 separate ions. Sodium sulfate produce 2 sodium ions, 1 sulfate ion. Aluminum chloride, AlCl3, produce 4 ions, Al3 plus and 3 chloride ions, 4 ions together. So this is something that you have to know about solubility when water, these substances, ionic substances, go into water, how they hydrate and go into solution. Some of the salts or sodium, like silver chloride, is a salt. It's not soluble in water. So we have to find out which ionic compound will not dissolve in water. The main reason, because they don't go into water, is that solvation energy release in breaking up sodium and chloride ion in the sodium chloride is larger than the energy required to break up the crystal. So when the crystal breaking energy is larger than the solution energy, they don't go into solution. They become insoluble. Simple generalization of ionic compounds allow us to predict their water solubility. This is simple table. You can argue why some salts are soluble based on charge, large charges, small cations and anion, etc. The solubility is, we probably gone over this little bit before. All salts of group 1 metals. Group 1 is sodium, potassium, lithium, sodium, potassium, normally most common. Group 1 metals and ammonium ions are soluble. All nitrates, anything that contains nitrate ion, So chlorides, most are soluble except silver chloride, mercury chloride, lead chloride. Mercury chloride is MgCl, HgCl2, HgC, mercury 2 chloride. Lead is PbCl2. Mercury, silver, and lead chlorides are insoluble. Sulfate are more, almost most of them are soluble. Strontium, barium, lead, and silver are exceptions. Barium sulfate is a commonly known insoluble salt. All other sulfate are soluble except strontium, barium, and lead, and silver. Carbonate are mostly insoluble except for group 1A and ammonia. And first listed in the table follows mostly. Hydroxide and sulfide, mostly insoluble except group 1A, group 1 metals, lithium, sodium, potassium, and ammonium hydroxide. KOH is soluble. Strontium is group 2, is insoluble. So you have to know this list, which are soluble and which are insoluble. If I ask you a question, is sodium sulfate soluble? Answer is yes, it's a group 1A. Is calcium sulfate is soluble? Yes, you will look under sulfate. Calcium is not one of the exceptions. The silver, strontium, barium, lead, and silver are the exceptions. Calcium sulfate is soluble. So you can look into the ionic compound and find out which one are soluble. When you mix up certain combinations of ions, you get the salts. So lead nitrate is soluble because nitrate is all soluble. Calcium sulfate is soluble. Sodium phosphate is soluble because sodium is group 1A. Aluminum hydroxide is insoluble because most hydroxide are except group 1A and ammonium. Silver bromide is insoluble because silver is one of the chloride, bromide, iodide are insoluble. So bromide, chloride rule applies to bromide as well. Now, when ionic compound dissolve in water, they produce ions. When they do that, if you check with the bulb with the current, with 2 electrodes put inside the solution, it lights up. Electrolytes are the solution containing ions like sodium chloride, sodium nitrate, calcium sulfate. They brightly light up the bulb. So they're called strong electrolytes. Non-electrolytes, which don't have like sugar solution, alcohol solution, these are ionic organic compounds which don't have charges. They are non-electrolytes. Sugar dissolved in water is non-conducting, it's a non-electrolyte. Sodium chloride in water conduct electricity, therefore strong electrolyte. There's a acetic acid solution, which is weak electrolyte. It's only partially broken up in the water, acetic acid. Only limited number of protons. Therefore, the bulb glows little bit, not strongly. Therefore, it's called weak electrolyte. So we can classify ionic compounds based on their solubility and their electrical conductivity in water solution. strong versus weak electrolyte, like sodium chloride, HCl, are strong. Acidic acid is weak. If a compound completely dissociates into ions in water, it is strong electrolyte. 100% of the substance break into ion in this case. If a compound partially dissociates into ion in water, a weak electrolyte. So that's example is acetic acid. Some of the substance break into ions, the rest remains as a whole. So weak acid bases also, we're going to talk about their dissociation is partial. If a substance dissolved in water but does not dissociate, break up into ions, these are non-electrolyte. So we talked about it. Table sugar, sucrose, dissolved in water but doesn't dissociate. Therefore, they are non-electrolyte. Sugar molecules, sucrose is shown here. Sucrose is a glucose and fructose. Fructose is a 5-membered ring here on the right side, and the glucose is a 6-membered ring. So since they have a lot of OH dipoles, sugar is full of OH groups. They dissolve in water through hydrogen bonding. The term like dissolve like is synonymous with similar. Dissolve is similar. Like means similar. So like is polar, dissolves in polar solvents. Water is a polar. Sodium chloride is also polar in a way because it has charged particles. Water dipoles also contains polarized charges. They can attract each other and dissolve. A polar compound, for example, ethanol has OH group, will dissolve in polar solvent, example water. Non-polar compound is oil, gasoline, etc. Oil is vegetable oils. In are organic compound, non-polar solvent, for example, gasoline. Gasoline will dissolve oil, but not the water. Non-polar compound will not dissolve in polar solvent and vice versa. Non-polar is like hydrocarbons, will not dissolve in water. Now we're going to look into certain aspects of compounds that produce acidity, which are called acids. Certain substances dissolve in water, break up hydrogen ions and produce hydronium ions. Acids are historically sour taste, like vinegar, and change the color of indicator or react with carbonate. So they react with carbonates, produce carbon dioxide. Gas evolve when you place acid on a piece of shell consists of calcium carbonate. So another way to define acid is substance that release hydrogen ions. That's a chemical description of it. Hydrogen ions are produced when they dissolve in water. Hydrogen ion in an aqueous solution cannot exist as hydrogen ion. It's a bare proton without one electron. Since the hydrogen ion has no electron and only one proton, hence the positivity charge, the hydrogen ion sometimes is called a proton. Consider the dissociation of hydrochloric acid. What happened to it when it goes to HCl breaks up into hydrogen ion and chloride ion. The hydrogen ions are solvated by AQ ions also we found out it reacts with water molecule and produce hydronium ion. Hydronium ion is the main component that hydrogen and aqueous means. Hydronium ion. Ions are much too reactive to exist alone. So they attract something else, water molecules. Protons attract to water molecules, so it's called hydronium ion. H3O plus, hydronium ion. When HCl dissolves in water, it produces hydronium ions, solvated hydronium ions, and solvated chloride ions. Chloride ions remain unchanged. Therefore, the correct way to show dissociation of HCl is HCl with water produce hydronium ion and chloride ions. Both are solvated by surrounding with water molecules. So hydronium ion is kind of a Lewis structure is shown here. It has that structure, similar to ammonia, but it's charged, positive charge. Let's take a turn into describe how all acid harmful. Some of the acids are taken orally is dangerous, like sulfuric acid, nitric acid. But vinegar, weak acids, are added into salads. Vinegar is acetic acid, diluted solution of acetic acid. Although word acid may conjure up all sort of pictures in your mind, every day you eat, drink various acids. Check the labels, food beverage, and make list of acid you find. Speculate on the purpose of each acid. Citric acid is an acid, organic acid, acetic acid, etc. There are several commonly used acids in food labels. So not all of them are dangerous. You have to read the labels. Bases are substances that dissolve in water produce hydroxide ion. Acid produce hydronium ion. So this label is about sodium hydroxide solution. Lye. Lye is a solution of sodium hydroxide. So we use sodium hydroxide to produce biodiesel. This is not something that you should be drinking or putting in the food. So food label need to be read. The flip side of the story is opposite of acids are bases, which contain hydroxide ion. Base is a compound that produces hydroxide ion in water. Aqueous solution is water. Unlike acid, which are bitter, which are sour, bases are bitter taste. We never recommend tasting anything in the laboratory or in the household if you know that is dangerous. The bases gives slippery feeling. When you apply soap on your body, it's slippery mainly because when you produce soap, a lot of sodium hydroxide, potassium hydroxide are added. There's somewhat that little bit of bases are left over, create slippery taste in soap. Unlike acids, bases turns red litmus paper to blue. Acids turn blue litmus paper to red. The sodium hydroxide, when dissolved in water, produce sodium ions and they separate, dissolves hydrated sodium ions and hydroxide ions, just like sodium chloride. Example of bases. Strong bases are where OH ions is completely dissociated in water. Normally group 1A, that means lithium, sodium, potassium. Group 2A, group 2 is magnesium, calcium, strontium, barium, hydroxide as examples of group 1A, 2A. KOH is a strong base. It dissolves in water completely. Calcium hydroxide produces 2 times OH ions. That's a strong base. What about ammonia? Ammonia doesn't have OH groups, but when you put that in the water, it breaks up water to hydroxide ion and ammonium ion. Therefore, OH ion create a basicity. Basicity is OH ions. Acidity is coming from hydronium ions. Since the reaction proceeds both directions, it is an equilibrium. It's a weak acid, weak base. Ammonia is a weak base. It's only limited number of ammonium ions. It's a weak electrolyte also because there are fewer ions in the solution. A neutralization reaction is reaction between acid and a base to produce water and salt. When acid and base react with each other, they are called neutralization. Hydrogen ions from the acid combine with hydroxide ion from the base to form water plus the salt. The other product is the salt. Hydrochloric acid with sodium hydroxide produce sodium chloride and water. Sodium chloride is a salt. Neutralization is as a net ionic equation, hydronium ions plus hydroxide ions produce water. We use ionic equation to describe this neutralization process. The reaction may be represented with the molecule ion or net ionic equation. Molecular equation, ionic equation, net ionic equation, we talked about that previously. You probably have forgotten. Molecular equation contains all the neutral species balance. Ionic equation separates out whatever dissolved in water, aqueous salts into respective ion. So if you remove spectate ions, you get the net ionic equation from the molecular net ionic equation, ionic equation. This is the molecular. It's this neutral species showing whether soluble or insoluble in water. All the ionic compounds are dissolved into separate ions. Only AQ could be broken up into ions. This is ionic equation. The spectate ions are ions that are found in both sides, bromide and barium. So they are spectate ions. Therefore, they are removed from ionic equation to get the net ionic equation. So when you remove bromines and barium ions from both sides, you end up with net ionic equation. Net ionic equation for neutralization is hydronium ion plus OH ion to produce water. Now we're going to talk about pH. pH is a way to show hydrogen and hydronium ion concentration. Hydronium ion concentration mathematically expressed as a number is called pH. pH of a solution is a measure of concentration of the hydrogen ion. This is hydronium ion. Hydrogen ions are hydronium ion. The mathematical expression for pH is log base scale and is represented as If you knew the hydronium ion concentration, that's square bracket hydrogen ion, take the log of that and change sign, you get the pH. Hydronium ion concentration or hydrogen ion concentration of water is 1 times 10 to the negative 7. If you take the log of 1 times 10 to the negative 7, you get negative 7. Multiplied by negative sign before the log. Negative times negative become positive, therefore pH of water solution containing 1 times 10 to the negative 7 hydronium ion is pH is 7. So you can calculate easily. You can undo pH given. You can undo pH to hydronium ion concentration. You change the pH sign, multiplied by negative, and take 10 to the x. Log, inverse of log is 10 to the negative, 10 to the x. 10 to the x undo log. So you can do these calculations. If hydronium ion concentration is 10 to the negative 3, pH is log 1 times negative 3, it becomes 3. Log of 1 times 10 to the negative 3 is negative 3 if you do with the calculator. So pH is 3. It's easy to calculate pH of a water solution. Since pH is a log scale based on 10, pH change of 1 unit represents a power of 10 change in the hydronium ion concentration. So pH is 0 to 14. Let me explain it a little later. This solution of pH 2 has 10 times that of a solution of, I couldn't see what is in there. pH 1 has 10 times more, 10 times that of the solution of pH 1. Now pH is mainly based on dissociation of water. Dissociation means water breaks up with another water molecules to produce hydronium ion and hydroxide ion. This dissociation equilibrium, let me see whether, this is not here shown in the dissociation equilibrium. Two water molecules react with each other to produce hydronium ion and OH ion. The product of water, ion product of water is the hydronium ion times OH ion concentration, which found to be 1 times 10 to the negative 14. Therefore, in neutral water contains 1 times 10 to the negative 7 hydronium ion plus 1 times negative 7 hydroxide ion. When you multiply these two numbers, 1 times 10 to the negative 7 by 1 times 10 to the negative 7, you get 1 times 10 to the negative 14, which is called the ion product of water, ion product constant of Kw. So this is used in mainly idea to get the pH. At neutral pH, hydronium ion concentration is equal to OH ion concentration. pH 7 is 1 times 10 to the negative 7 hydronium ion concentration. Therefore, OH has to be 1 times 10 to the negative 7 to get the ion product constant 10 to the negative 14. Acidic solution is pH is less than 7. We know that 7 is neutral, neither acidic nor basic. Less than 7, 7 to 0 is acidic. Most acidic is as you go through approach 0 in the pH scale. The most basic is as you approach 14. 14 is the most basic pH. The pH is only between 0 and 7 for water because it's decided by dissociation equilibrium of ion product, or Kw. pH scale is used as it measures acid over many orders of magnitude. So pH scale avoids 10 to the negative powers. So if a solution has 10 to the negative 4, pH is 4. So you can exactly calculate, put in the 1 times 10 to the negative 4, or whatever that number is for the hydronium ion. pH will not be always whole number. You take the minus log of, you take the log of hydronium ion concentration and change the sign, you get the pH. If you look at pH scale, the blue color is basic pH. The red color is acidic pH on the left. 7 is the neutral, which is pure water based on ion product constant. Milk is slightly acidic. Tomato juice is about pH 4. Cola is, carbonated drinks are acidic. It's about 3. Lemon juice also acidic. The stomach acid is most acidic. So if you happen to throw up once in a while, you will feel how bad the stomach acidity is. Your teeth get kind of that feeling when you drink a strong acid. That is what the strong acidity does to your teeth and mouth. The blood and the biological pH is below 7. Seawater is about 8. See, there's the idea that we grew up in the sea and evolved to the land, that our still bodies maintain pH very close to oceans. Milk of magnesia have higher pH. It's a basic. It's used as antacid. You drink milk of magnesia, your acidity is neutralized in the stomach. Hydrochloric household ammonia is basic, but you don't drink ammonia or lye. Lye is sodium hydroxide. It's the strongest, 14 pH, a base. Compare the pair of example for each which is more acidic. Include the relative difference in hydrogen ion concentration between the two pH values. Rainwater, pH is 5. Lake water is pH is 4. Rainwater is less acidic than lake water. Lake water accumulates acidic water and become more acidic. pH 4 is more acidic than pH 5. Ocean water is pH is 8.3. Tap water is 5.3. Tap water is acidic. Tomato juice is 4.5. Milk is 6.5. So tomato juice is more acidic than milk. The rainwater is naturally acidic. When it rains, carbon dioxide dissolved in water, carbonic acid produce acidity. Carbon dioxide in the atmosphere dissolved to a slight extent in water and reacts to produce slightly acidic solution of carbonic acid. The carbon dioxide dissolved in water produce carbonic acid, H2CO3. The carbonic acid dissolves slightly, leading to rain with pH around 5.3. So the normally rainwater is about 5.3 pH, slightly acidic. Let me go back. So carbonic acid breaks up into hydrogen ion, which is turned into hydronium ion. That's the acidity is coming from that I missed in the last. We need to know about acid rain. Acid rain is caused not by carbon dioxide to increase the hydrogen ion concentration in rain. When you burn fossil fuel, which contains sulfur, and also fossil fuels produce nitric acid, when the cars run at higher temperatures, convert nitrogen and oxygen to nitric oxide, cause ozone, secondary ozone, and pollution, smog, and etc. So these sulfur and nitrogen oxide compounds, when dissolved in water, produce sulfuric acid. Sulfur trioxide converted to sulfuric acid on acid rains. And nitric acid, also produced by nitrogen oxides, which react with water and get oxidized, nitrogen dioxide, so produce nitric acid. So that what happened to forests? Some of the forests exposed to nitric acid the plants die, cannot withhold the acidity, so they die and cause forest destruction by acid rain. This acid can have downwind and anthropogenic or natural resources of SO2 and nitrogen dioxide. So there are natural sources also. Volcanic action also produce sulfur dioxide. That's why it's called natural sources. Anthropogenic is man-made, like burning coal, which contain high amount of sulfur, cause more acid rain. Now let's talk about ocean pH. Ocean pH is 8.3, we talked about it. If rainwater is naturally acidic, why is oceanic water basic? It is because carbon dioxide dissolved in water produce bicarbonate ion, which produce basic pH. 3 chemical reactions responsible for maintaining pH of oceans. First one is the carbon dioxide carbonate ion. Other one is bicarbonate ion and carbonic acid. These 3 compounds take a part in equilibrium with each other and maintain a pH of 8.3. So oceans pH is decreasing due to increased atmospheric carbon dioxide. So atmospheric carbon dioxide create acidic pH. The carbonates are necessary for marine animal shells and skeletons. So carbonate ion is react with hydrogen ion produced by carbon dioxide, carbonic acid, and react with carbonate ion in seawater. So carbonate ion produced from animal shells, seashells, react with acid and produce bicarbonate ion. So that bicarbonate ion dissolves calcium carbonate in C cells more. Calcium carbonate C cells creatures begin to dissolve to maintain the concentration of carbonate ion. The carbonate ion is removed to bicarbonate, therefore it need to be replaced. Then C shell had corals and other sea creatures which have calcium carbonate covering, as a result, would die. So that's a habitat disruption. So calcium carbonate is produced by dissolving seashells, calcium carbonate to calcium ions and carbonate ion. So ocean acidification continues as we use fossil fuels. Carbon dioxide release, those three equilibria are shown in the picture in the ocean. Therefore, ocean acidification is a problem, not only on Earth, also on sea, on the oceans. Over the past 200 years, the amount of carbon dioxide in the atmosphere has increased. So more carbon dioxide is dissolved in the ocean and forming carbonic acid. So therefore they dissolve carbonate and to maintain the carbonate ion in the ocean. So aquatic life requires certain pH. Acidification of water is also taking place in lakes and streams. Midwestern states has certain amount of limestone. Therefore, acidification is neutralized naturally by calcium carbonate, like in sea floor in the ocean. The coal acid neutralization capacity of Midwestern countries are higher than other states. Some state has more granite type calcium carbonate, which is much less reactive. Lakes and streams are more sensitive. So figure below gives the pH of different normal aquatic life is pH is 8. Life disappears at pH 5. Many fish disappear at pH less than 6. Most lakes are dead around pH 4. Therefore, this acidification of lakes and streams is a problem. It same as the oceans will create coral reefs to disappear and calcium carbonate to creatures to dissolve. So reducing the aquatic life in ocean and both oceans and lakes. Now we're going to look into how we treat our water in municipal plants, water treatment. What we do is we put the wastewater into a lake and let it settle down, filtration. And we also use filtration and add certain chemicals to remove particles from the water. Alums, aluminum sulfate, and lime are used to precipitate fine particles. Charcoal and sand pass through charcoal and sand filters to remove organic substances that are contaminated in wastewater. aeration. We pass it through the air, like the most municipal power plants had aeration. You mix up air with the oxygen in the air. It removes also volatiles. Aeration removes volatiles. Calcium decreases the acidity, calcium oxide. Chlorination is used with sodium hypochlorite, which is a source of chlorine to kill microbes. We also use ozone and UV light naturally through the lamps or by the sunlight. So all these processes clean up the water, and then we pump water into storage and supply into communities. There's another way to make fresh water from salt water. It's a distillation by heating up water, but this is expensive. You can distill, you have to use heat. So distillation is a process we use in our labs to produce distilled water that are used in many chemical reactions. Pure water is distilled water. There's another process which is called reverse osmosis. You pass water through a semi-permeable membrane by applying a pressure from concentrated to dilute side. This is the reverse of osmosis. You have to have a high pressure pump to pass water through the semi-permeable membrane. Many Middle Eastern and Israel, these reverse osmosis take place. They produce about 14% of water supply. Reverse osmosis uses the pressures to force the movement of water through a semi-permeable membrane from solution that is more concentrated to solution that is less concentrated. So this is another source of fresh water. We have finished the chapter 8. I'm going to put, you can find the questions and answers on the module 4, go through them and get ready for the exam for test 4 for chapter 7 and 8. All right. I'm going to send an email announcing about the test date for chapter 7 and 8.